All right. Now we're going to do linear systems in more than two variables, excuse me. Here is a 3x3 linear system. It has three equations and three unknowns, therefore 3x3. You can check a solution by substituting x. And as before, A, B, C, D, E, F, G, H, I, J, K, and L are constants known, and X, Y, and Z are the variables to discover. And you can check a solution by substitution. We solve by elimination. As before, we use row operations to eliminate variables. Row operations are rescaling and combining. If A equals B, then you can rescale to get KA equals KB. You have two equations, and you will add K times equation 2 to equation 1. Get X plus KA plus KC equals B plus KD. And C is still equal to D. So you use row up, excuse me, that was not required. I don't know how that happened, apologies. We use row operations to eliminate variables. Then, okay, there's back substitution. Here we have a system in what's called triangular form, like this. This is lower triangle, lower left triangle, the part of the triangle is all 0. So negative 2x equals 1, so z equals a half. Substitute into the equation just above it. Y plus 4 times negative 1 equals 2. That's called back substitution. So y minus 2 is 0, so y equals 2. Then having gotten y and z, we substitute into the first equation, or back substitution to solve for x. 2x minus 2 plus 6 times minus a half equals 5. And so I could just do a little bit of algebra. 2x minus y minus 2 minus 3 is 5. So 2x equals 5 plus 2 plus 3. So 2x is 10. So x equals 10 halves or 5. So there you go. X is 5, y is 2, z is minus a half. This triple is the solution. And remember, you have to give all x, y, and all the variables to make a solution to a system. A system consists of several equations and several unknowns. So you need to give all the solution requires telling all the unknowns that satisfy together all the equations. Now, here we have a hard one. Okay, a complete 3x3 system. And the problem with 3x3 systems is more than twice the number of numbers in it. I mean, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 numbers, whereas 2x2 will only have 6 numbers. So you have at least twice as much work, unfortunately. So, all right, we're going to solve by elimination. Now, this is a whole process, and I'd need for you to attend. We start with this x here. It has a 1 in front of it. That makes it easy to work with. What we're going to do is to clear the rest of its column, get rid of these two x's by row operations. So if you have a 2x minus twice e1, 2x minus twice x will cancel to get a 0. And you have a 2x, so we subtract twice equation 1 from equation 3. Again, 2x minus twice x cancels, eliminates that variable. Now the other variable, the other things, they come along for the ride, so we have to work with them, and we have to do a bunch of calculations. Okay, first row stays the same. X plus y plus z equals 4. That's good. Now for here, y minus twice negative 3. I'm sorry. Sorry. No, that's not quite right. Y minus twice y is negative y, so we put a negative y here. Negative z minus twice z is minus 3z, so we put a negative 3 here. 1 minus twice 4 is a negative 7, so we put a negative 7 here. Now for this one, again, the x's cancel. Negative 3y minus twice y is negative 5y, so we put that here. Z minus twice z is a negative z, so we put a negative z here. And 1 minus twice 4 is a negative 7, so we have a negative 7 here. Now we have the system. X plus y equals z equals 4. Negative y minus 3z is negative 7. Negative 5y minus z equals negative 7. Okay, first we'll rescale these two equations, second two equations, by a negative 1, just to make it, I'll give them all positive signs. So x plus y plus z is 4, y plus 3z is 7, 5y plus z is 7. We'll pivot on this y. In other words, we'll use row operations to null out this y here and this y here. So for the first equation, if we subtract equation 2, you get y minus y, cancels, all right? And z, just a second. Oh, and then z minus 3z is a negative 2z. Put a negative 2z here. And 4 minus 7 is a negative 3, which we put here. So this first equation becomes x minus 2z equals negative 3. Second equation, we keep the same. Y plus 3z equals 7. Third equation, 5y minus 5 times y cancels. Now, z minus 5 times 3z is a negative 14z. We put that here. And 7 minus 5 times 7 is a negative 28. We put that here. Now we have, getting there. Negative 14z equals negative 28. We divide by negative 14 and get z equals 2. Along with these equations, x minus 2z equals 3, negative 3, and y plus 3z is 7. Okay, now we'll pivot on the z. In other words, we'll use row operations to eliminate this negative 3z and this positive 3z. We have a negative 2z here. If we add twice equation 2, twice equation 3 here, we'll just I'll eliminate that x. So let's see. And here we have a 3z here, minus 3 times z. We'll cancel that. And okay, there's no x or y, so they don't affect this x and y at all. And finally, there's the constants. Negative 3 plus twice 2 is 1. We put a 1 here. 7 minus 3 times 2 is a 1. We put a 1 here, and we still have z equals 2. And now we've cleared out all the columns. And so you get x equals 1, y equals 1, and z equals 2, and that's a solution. Okay, the rest of these are much the same thing. It's just a certain amount of drudgery. And here's a word problem where the first step consists of turning it into a linear system, and followed by a great deal of work. Let's see what we can do here. Where are we at? Okay. Back substitution, not this. Now here we have a whole system. 7a plus 9b minus 2c equals negative 5. 5a plus 14 minus c equals negative 11. 2a minus 5b minus c equals 3. Okay, it comes too much of a muchness. All right, here's what we do. Let's just, here I rescale the third equation by a negative 1. So in order to turn this negative c into a positive c, which we can now pivot on. If we add equation 2 to equation 3 to equation 2, that c cancels out. If we add twice equations 3 to equation 1, that c cancels out. And okay, 7a plus twice negative 2 is a 3a, goes there. 9b plus twice 5b is 19b, so that goes there. And negative 5 plus twice negative 3 is a negative 11, so that goes there. 5a plus negative 2a is 3a, that goes there. 14b plus 5b is 19b, so 19b goes there. And negative 11 plus negative 3 is negative 14, so negative 14 goes there. All right, here we go. We have this system here. Uh-oh, trouble. 3a plus 19b is negative 11. 3a plus 19b is negative 14. Uh-oh, we're running into trouble. And in fact, we can see that if we take this first equation and subtract the second equation from it. 3a minus 3a cancels. 19b minus 19b cancels. Negative 11 minus negative 14 equals 3, and we get 0 equals 3. Now, this other stuff is still along, but that doesn't matter because we got an absurdity here. So this original system has no solution, because if you assume it, you get 0 equals 3, and it's not. So there's no solution, which is what happens if you ever get negative non-zero equals 0. So this original system here has no solution. Here we have an underdetermined situation. We have a linear system here. You have terms on variables on both sides. We do some transposing, and we get 2x plus 3y plus 4z equals 6. 2x minus 3y minus 4z equals -4. 4x plus 6y plus 8z equals 12. Okay, great. Okay, first, well, we rescale this third equation by dividing by 2. 2x plus 3y plus 4z equals 6. 2x plus 3y plus 4z equals 6. 2x minus 3y minus 4z equals -4. 2x plus 3y plus 4z equals 6. Uh-oh, the first and the third equations are the same equation. So if we combine by subtracting equation 3 from equation 1, you get 0 equals 0. So and we already knew that. This does not give us any information. So really we have only 2 pieces of information, but it's for 3 variables, and that's not enough. So therefore, there are many solutions. It's underdetermined. There's not enough information. So that's what we get. If you ever get 0 equals 0, then it's an underdetermined solution system with many solutions. If you get 0 equals non-zero, then it's an overdetermined system with no solutions. Okay, this last step. Okay, here we have a word problem, and those are always the most annoying of all. So I'll devote most of our attention here to setting up the system, and then briefly running past the solution. Here we go. We have 3 kinds of smoothies: Midnight Mango, Tropical Torrent, and Pineapple Power. Some would like alliteration. And we have each has various amounts of juices. Midnight Mango is 8 ounces mango juice, 3 ounces pineapple juice, and 3 ounces orange juice. Tropical Torrent has 6 ounces mango, 5 ounces of pineapple, 3 ounces of orange. And Pineapple Power has 2 ounces mango, 8 ounces pineapple, and 4 ounces orange juice. And they use 820 ounces of mango, 690 ounces of pineapple juice, and 450 ounces of orange juice. How many smoothies of each kind did they make? Now, as ever, when dealing with a word problem, the very first thing to do is to give names to the things you're trying to find out, to assign variable names. And they're asking how many smoothies of each kind. So let X be the number of Midnight Mango smoothies, Y be the number of Tropical Torrent smoothies, and Z is the number of Pineapple Power smoothies. That'll answer this question. Then you sum 8x plus 6y plus 2 equals how much mango? 820 ounces. 8x plus 6y plus 2z equals 820. That's how much mango is used. That's for pineapple juice. It's 690 ounces. That's 3x of this. It's 5y here plus 8z here. So 3x plus 5y plus 8z equals 690. Use 450 ounces of orange juice. So 3x plus 3y plus 4z equals 450. Get the system here. So here we have a 3x3 system. 8x plus 6y plus 2z equals 820. 3x plus 5y plus 8z equals 690. 3x plus 3y plus 4 equals 450. Okay, great. 3x3. All right, now we use row operations. We divide the first row by 2 just to make these whole numbers. Just reduce the numbers. All right, here we have a 1z. We'll pivot on this. So to eliminate this 8z, we subtract 8 of equation 1 from equation 2. To limit this 4z, subtract 4 of equation 1 from equation 3. And after a fair amount of work here, the z column is cleared, and the rest becomes these numbers here. We have a negative throughout. Let's rescale by -1, and interesting. I subtracted equation 2 from equation 3. I guess to make things come out kind of nicer. And in fact, these have a common factor of 10. And this is this. After, okay, great, we get down to single y here. And we use it to clear away this column here. And we get this system here. And here we have 1 minus 1.4x equals -70. So we divide both sides by -1.4. So you get x equals 50. I use some row operations to clear out its column here. we get this kind of messed up a bit. So we swap things around and get x equals 50, y equals 60, and z equals 30. So going back to the original definitions, that means they made 50 midnight mangoes, 60 tropical torrents, and 30 pineapple powers. And yes, 3x3 systems are twice the work, at least, of 2x2 systems. Unfortunately, I don't know any way around that. So that concludes that.